talking about black holes and relativity. So, what are black holes? Well, in 1783, John Michel, he proposed the idea of black holes because he thought there had to be an object so massive that its gravitational pull was so strong that the light emitted from this object had to be sucked in. So today I'm going to be describing non-rotating uncharged black holes, also known as Schwarzschild black holes, which I'll talk about later. But what black holes are is any object with mass that is compressed into the Schwarzschild radius, which means that all of you could be black holes. Even that chair could be a black hole. If it was compressed to the size of an atom, it could be a black hole because all black holes are is a sphere of compressed mass. Inside a black hole is a singularity, containing infinite density and gravity. So here is the basic anatomy of a black hole. First we have the photon sphere, where it's a stable orbit for the light to orbit around the black hole where it's not too close and not too far from the event horizon. Because past the event horizon, you have to have the escape velocity, or also where escape velocity is where you can escape an orbit of an object. For example, for Earth, you need 11 meters per second to escape the Earth's orbit. And to escape a black hole's pull, you have to be faster than the speed of light. So escape velocity has to be faster than the speed of light. And then after that, you are just headed to oblivion, which is the singularity. And the size of the black hole is the Schwarzschild radius. So what is the Schwarzschild radius? Well, this is the equation for a Schwarzschild radius, where r is the radius equals to 2, where g is the gravitational constant, and the mass is the object that's going to turn into a black hole divided by the speed of light squared. This explains why black holes are so small, because the speed of light is just so great that squaring it just decreases the size of the radius. Based on this equation, the greater the mass, the greater the radius. So to talk about how the nature of black holes work, we're going to touch upon special relativity and general relativity. So what is special relativity? Well, before general relativity was published, Einstein published a theory that talked about motion called special relativity. So special relativity has two postulates. One is that the laws of physics are the same in all inertial reference frames, meaning that the laws of physics apply to no matter where you are if you are in a constant velocity and heading towards a straight line. For example, if you were on a train that was in a constant speed the entire time, and you were measuring the size of a piece of wood, it would be the same even if you were outside, not moving at all. The second postulate is that the speed of light is constant for all observers. So the same thing that I said before, except for the speed of light, that the speed of light is always the same no matter what. Many of you know this equation where speed times time is equal to distance, where speed in this situation is constant because it's the speed of light, which we said was constant. So d is the distance and t is the time. So if we want to maintain the same distance and we want to remain the same speed of light because it's always constant, then what's changing is time. So as you increase the speed, time decreases. As you can see in this train, there are two clocks, one in motion, one not in motion. One clock is on the train, one is not. As the train moves, the time has to decrease for the train, so the distance is always the same. This is called time dilation. But time cannot only ensure the speed of light has to remain constant. There's something else that happens. That's called length contraction, which we'll come to later. So this is, let's just imagine a rocket. And at the bottom of the rocket, there's a light beam that aims at a mirror on top. And the light bounces back and forth in this rocket. Now, there is an astronaut in this rocket. And he'll be our reference one, the astronaut. And our reference two will be this boy observing this rocket. So the perspective of the astronaut is that the light moves up and down, all right? So that's his perspective. But this perspective of the boy is that he sees the light actually moving a longer distance to reach the endpoint than what the boy sees. So how can this be possible? How can light travel a longer distance to reach its endpoint than what the astronaut saw? Well, this is how time dilation and length contraction come into play. Like we said before, as speed increases, time decreases. So for the rocket, it's a slower time than what the boy perceives. So the light will have greater amount of time to reach its endpoint. It will have more time to reach its endpoint since the time is decreasing from it, while the astronaut sees light go up and down. Another thing that happens is called length contraction. As speed increases, also length of the rocket actually decreases. So that also helps compensate for the speed of light, because the light has to travel less of a greater distance than it did before. So that's why both length contraction and time dilation is important. That's why it's called space-time, because both space and time is affected. So this is the equation for time dilation, where T prime, with the comma, T prime is the time that the astronaut perceives that the rocket is going to reach its endpoint. And T is the time that the boy perceives that the rocket is going to reach its endpoint, and divided by the speed, where velocity is the speed of the rocket. Now, if you look at this equation, if the speed of the rocket was actually equal to the speed of light, which is represented as c, then t would be divided by 0, which means that the speed of light is infinite. We'll go for infinite. And also, if v was greater than the speed of light, then it would be a negative number, and it would be an imaginary number, which means that it's not possible to go faster than the speed of light. Now we're going to talk about general relativity, which was published in 1916 by Albert Einstein, where he applied gravity to his equations. So what he said was, near an object with immense amount of mass would slow down time. So what does this mean? Well, I have mass, so I work time. But the reason I don't have a gravitational field, why you can't feel that gravitational field, is because I work time by a minuscule amount that you can't feel. Something as massive as the Earth, for example, or the Sun, warps time by so much that it has its own gravitational field and affects objects around it. So what is space-time? Space-time is combining the 3D space, the 3D that we are seeing each other, and then also time. So that means time is a dimension, which means we live in a 4D world, but we only perceive the 3D world. So how can time be 4D? Well, this is what would happen if we could see the 4D world. We would see everyone's timeline. If I was walking from this point to that point, you could see my entire path, how I got to this point. But we can't see this because we perceive things one at a time. Only some godlike being out there, out of space-time, could see this. So let's imagine another thing. Imagine a black hole, right here, and an astronaut, right there. And this astronaut is at a safe distance from the black hole. And there's an alien that's going to be traveling inside the black hole. So, as the alien nears the black hole, what the girl sees is that as he nears the black hole, he actually slows down as he goes closer and closer to the black hole. Because, like I said again, mass affects time. It slows down time. So, for the alien, time is decreasing, but he doesn't notice this. He thinks time is going at the same speed, but if he looks at the girl, time is actually elapsing. If he looks at the universe, the entire universe behind him, he sees the entire future of the universe going elapsed time, because for him, time is going faster for them. So, as he touches the horizon of the black hole, what the girl sees is he actually doesn't enter the black hole at all. Even if she was immortal, she will never see him enter the black hole. In fact, he's invisible to her. Because light is redshifted by so much that it will never reach her. That, like I said before, black holes suck up light, and they don't let it out. So the light inside a black hole will not be emitted to her, and she will never see him. But in his perspective, he goes inside the black hole. he gets sucked up and dies. But, well, I don't know that. But, what she sees is something different, that in our universe that event never occurred. So some people think that a black hole is just a bunch of events that never happened in the first place. That's why it's black and empty, because it's just events that never even happened. Okay, so this is a light cone. Let's just say that this dotted line right here is the speed of light. And that's what limits us from the past and the future. This is where we are, and this is the future light cone. This is where all events in your future will happen, which has to be less than the speed of light. This is your past light cone, where all these events that happened in your past affected what happened in your present, like what happened right now. So that means you can never get to the past, because to cross this point, to get over here, you have to be faster than the speed of light, which we already said that was impossible. So what I'm saying is time travel is not possible. Time travel is possible to the future. Like I said, when we decrease time, like someone near a black hole, 2 weeks for them could be 3 years in Earth. So that's like going into time in the future, but you cannot go to the past, because that would affect the present. And going to the past is not possible, because when you enter a black hole, your future light cone is all directed towards the black hole, because your future is going to be inside the black hole because you cannot escape it. But the past is directed out. So the only way out of the black hole is going back to the past. So that's why you have to be, the escape velocity has to be greater than the speed of light to escape this way. Oh wait, why are black holes important? Well, black holes are important because they make up our universe. Without them, we wouldn't exist. Why? Because there is something called supermassive black holes, which are black holes that are larger than regular black holes. And they're in the center of quasars. And quasars make up our galaxy. And the center of our galaxy is a supermassive black hole. And many other galaxies, every other galaxy has a supermassive black hole. Because that's how they form, by an accretion disk that a black hole makes. So, well, we don't know a lot about black holes, and I don't think we'll ever know what really happens inside a black hole. Because, like I said, you cannot send a signal inside a black hole, so I think the only way to really know about the singularity is if you actually travel inside a black hole. I want to thank Junction, and I also want to thank my mentor, Emily, gave me a lot of insight about special relativity, because it's really cool, about special relativity paradoxes. Those are really fun and interesting. And I want to thank my peers in my group, and I also want to thank my family for supporting me. Thank you.
Does anyone have any questions?
Yes?
How does the black hole die?
Okay. So there's something called Hawking radiation that is theoretical. It's not proven, because we only seen black holes have an accretion disk. We haven't seen them without just sitting there. So, can I use this board?
Yeah.
All right. So we have a black hole. Next to the event horizon, there's an empty space. An empty space is where there's two particles. One is positive, one is negative, where what they do is they disappear, then they come back again, combine again, basically commit suicide with each other, then separate, then do it over and over again. What happens is near the event horizon, the negative charged particle actually gets sucked in, and the positive charged particle can actually escape. And so what happens is, in Hawking radiation, more negative particles are sucked up in this black hole, and that's why it decreases in size and then eventually evaporates.
Other questions?
So when you said length contraction, were you talking about the Lorentz contraction or something else?
I was talking about the size of the object that is in motion. But yes, there it is. Yeah.